All right, we're working on 9-4. We're still working on rotations. I'm on page 124. I want to just kind of talk you through what this says. We've demonstrated it already in some of the other problems that we worked, but part of the what you should be learning when you take this course is how to read what at first appears like extremely confusing information and make sense of it. That's the thing about it. Students who are mathematically inclined kind of have this mathematical intuition. They kind of understand the math, but when they start trying to read it, they don't know how to make sense of what's being said about something that they already understand. So we're going to practice that. So this says that if you're not on a coordinate plane and you don't have ordered pairs to help guide you from the pre-image to the image, then these are two things that are going to be true. If you have a rotation and it maps your pre-image some point P to P prime and another point Q to Q prime. So P and Q are on your pre-image, P prime and Q prime are on your image. These two things are always going to be true. Now it says, oh yeah, by the way, we're rotating it about point O. Okay, so O is the center of rotation. So a distance is going to be equal to each other. We've got this distance, these two things that are equal, and these two things that are equal. And then we've got some angles that are equal. So I'm going to jump over here and put pictures to this so that we can actually rotate it. Okay. So here's the pre-image, PQB, and this is a rotation that I've done. And it is P prime. So P mapped to P prime, B mapped to B prime, and Q mapped to Q prime, and it rotated about 0.0. So here's what it said, and like I said, we've demonstrated this in previous videos. Here's what it said: the distance from whoops, I did the wrong thing. The distance from here to here, from some point, and it doesn't matter which one, the distance from this point to this point will always equal the distance to its image to the point of rotation. And we showed that on another one, on another example, but I'll show you here. Okay. And I think hold on, let me see. I think we showed that if we moved it, it didn't matter where we move that point, that the distances stayed the same from the pre-image point to the center of rotation to the image point to the center of rotation. Those two measurements remain the same. So that's what Springboard is saying right here. And I just drew this one, but this one's going to be the same thing. Just for sake of time, I'll do it real quick. It's a segment. So we're going to go here to here and Q prime to Q prime, and we'll measure it. Okay. And so even if you move this one, see, they stay the same. You move this one, the measurements stay the same. So that's all Springboard is saying. So everything that was true on the coordinate plane is still true if we're not on the coordinate plane. And what is this saying? The angle measure between them, the angle measure between those two segments will be the same angle measure as that one. And you guys should also be able to tell me what those angle measures are going to be, right? Well, it's going to be whatever the angle of rotation was. You didn't see me rotate it, and I don't even remember what I rotated it. So I'm going to measure one of them and see. I think if I do this one right here. Oh, I rotated it 90 degrees. So that one came out to be 90 degrees. And this angle right here came out to be 90 degrees. And if I measure this angle right here, guess what it's going to be? It's going to be 90 degrees. So I'm going to measure the angle. And you can see it came up to be 90 degrees too. So that's all Springboard was saying. So the same things that we learned about it on the coordinate plane is going to end up working if you're not on a coordinate plane, if you're just on an unmarked piece of paper. Okay, so let's get to the notation. So here's the notation. Remember, translations were a capital T. Let's review. Translations were a capital T with a little with numbers down here. Let's say 2 and 0. That means that I'm going to translate it or shift it 2 units to the right and up 0. The lowercase script r was the reflection, and what we put down there is in subscript was the line of reflection. And then this is showing us that an italicized or a script capital R. The subscript right here is going to be the point of rotation, and then there's going to be some degrees. Okay, so it's going to be a capital R, a capital script R. It's going to be the point of rotation, and it's going to be some degrees. Let's say 90 degrees. Now, I believe it reads somewhere that if there's not a point of rotation, then it's understood to be the origin. But you know what? That may not be this textbook. So just know that if you run into it and there's no point of rotation, then that's going to be the origin. Now, another thing that you're going to need to know is notice in this notation, there's nowhere for it to tell me whether it's clockwise or counterclockwise. So that we know that that's 90 degrees, okay, I give you, but which direction should I rotate that, clockwise or counterclockwise? So what mathematicians did to keep from having to write clockwise and counterclockwise, they came up with positive and negative numbers. So if you rotate clockwise is negative, and I think when they use m above, negative m degrees. And counterclockwise, which goes this direction, okay, counterclockwise, that's positive m degrees. So right here where we see negative 90 means they want me to go clockwise 90 degrees. Down here, it says positive 90, so positive 90 wants me to go counterclockwise. And positive 90 also wants me to go counterclockwise. That right there is counterclockwise. And that's it. So you might want to take notes right here on this one. Clockwise is a negative degrees. Counterclockwise is positive degrees. All right, so I put this picture and this question over here so we can follow the directions and do the rotations. So I'm going to click here to rotate about a point. This is telling me the capital R is telling me I'm going to do a rotation. I'm going to rotate. I've selected the shape. This tells me that my point of rotation is O. So I've selected that. They wanted me to go, can't see it anymore. They wanted me to go, I think that was negative 90. So negative means clockwise and 90. And you press OK. So A was here, and it rotated 90 degrees, and it's negative 90, so we went clockwise. And C went clockwise, and B went clockwise. Okay, so they all moved 90 degrees. Let me erase that. And now I'm going to move that. Oh, good grief. I should have just backed up. Okay, now this one, they want me to rotate. Okay, so I'm going to rotate the triangle around point C. So I'm going to select point C, and it's positive 90. So it's a positive 90, and positive 90 means counterclockwise. So we press OK, and I rotated around C. I went counterclockwise, so A rotated to A prime, B rotated to B prime, and since I was rotating about C, C didn't move. All right, let's do the last one. We're gonna, this says we want to rotate, so I'm rotating the triangle. My point of rotation is A, and they want me to rotate it a positive 90 degrees. So 90 degrees, and positive means counterclockwise. Okay, so A mapped to itself, A mapped to A prime, but B went counterclockwise. So we go counterclockwise 90 degrees. So see the 90-degree angle between this line and this line. And then C, C also went 90 degrees. So if you notice the angle between this right here and this right here, there's your 90-degree angle. It rotated counterclockwise 90 degrees. Okay, the last one on this section of Springboard says describe 3 rotations. And so they're looking for this kind of notation. This is what your answer is going to be. Describe 3 notations that map a square onto itself. So here's a square. Well, we know that we can go either direction. We can go this direction, or we can go this direction, and it'll look like the square mapped itself. So I'm going to suggest that it's going to be a capital R. You can pick, I've picked the point E right here, which is in the center of the circle, the center of the square, because that's the easiest to map onto itself. 360 degrees will always map anything onto itself from any point of rotation. So that would be kind of a cheat answer. You could pick any point and rotate it 360 degrees. But if we do point E, which is in the center, we can map it a positive 90 degrees. Just to have a comma right there. So I'm gonna rotate this around point E. I'm gonna go 90 degrees, and I'm gonna go positive 90 degrees, so that's counterclockwise. And can you even see it? Let's see. Let's do it again. Let's do this around E, and let's go 45 degrees to make sure that it's actually happening. Okay, so see, it's actually happening. Why can't we see it? Because it's mapping onto itself. I'm surprised that it's not showing us where A prime is. It usually relists something as A prime, but it didn't. So as you can see, when we did it around E, what else would work? If we did this around this, what if we did 2 rotations of 90, 180 degrees? Did that work? Evidently, because it mapped it right back onto itself. So you could, then there's a bunch of different answers. So don't think there's only one. So I can do R about point E, and I did 180 degrees. Or you could do R about E and do negative 90. So there's three, but there's a bunch of different ways. You could also do, like I said, R around any point and go 360 degrees. That's the easy cheat answer. That always maps something back onto itself. So let's see if we can see it. Let's map this around A, and let's do 360 degrees. Let's go clockwise. And there it is. You can't see a difference because it mapped it right back onto itself. All right, so I'm going to stop this video, and we'll have one last video over rotation symmetry, and then we will finally be done with this series.